I think this will take up the whole class. These topics, you can see that there's not many of them. There's only 9 topics. You know, it's not like the mechanics in semester 1 where I think there was 26 topics, 24 topics. Yeah. So there's a little bit less pressure in semester 2. A little bit less. Okay, specific heat capacity. Next year they will make semester 1 a little bigger and semester 2, and semester 2 a little smaller. So it'll be even more difficult.
The question is more easy or more difficult?
No, what they're doing is they're swapping some topics. So they're making semester 1 a little bigger and semester 2 a little smaller, but this is bad because semester 1 you have less time and semester 2 you have more time. So semester 1 would be more difficult next year.
Yeah,
That's
just next year.
This is good for you. Right, specific heat capacity. Not yet. No. It sounds like capacitor and capacitance, but it's different. Yes. Capacitor, capacitance, and now capacity. Yes.
Capacity is like a keyboard.
It's like what?
Keyboard.
Capacity to give, maybe, but we don't use it for so much for giving.
Hold something.
Yeah, more like to hold something. Yeah. Okay. So, question: why does metal feel colder than plastic?
Because metal has a higher specific heat.
No, don't use.
It's easier to it has stronger.
Very good, thank you. It's easier to transfer heat to a metal than it is to a plastic. So it's the same reason that water at 10 Celsius feels colder than air at 1 Celsius. So if you picture this, if outside it's 1 Celsius, that's cold. But if you go out with your coat, you'll be okay. However, if you go into water that's 10 Celsius, no good. That will feel much colder.
With your coat?
With your coat, yeah. So why does the cold water of 10 Celsius feel colder than the air of only 1 Celsius? Again, the same reason. The cold water, it's very easy to take heat from your body. Your clothes get wet and the heat comes out. Not so easy for the air. So, clearly temperature is not enough. We can't just say how hot or cold something is. There's something else that we need to think about. Metals will feel hotter sooner than plastics. In fact, conductors will feel hotter than plastic. So you've done conductors and insulators with me, and you've also done them with Lorraine. Conductors can take heat very quickly. Plastics can take heat slowly. Some materials get hotter faster than others, and different materials have different capabilities to take the heat. So we have to have this idea of what's called heat capacity. So heat capacity of a material is how much energy you need to make 1 unit mass, 1 unit temperature hotter. So wait, before you write that down, let me just draw that as a picture here. So imagine here you have 1 kilogram and you would like its temperature to increase by +1 Celsius or 1 Kelvin. So you need to give it energy, correct? So you put some energy into it and it will get hotter. The energy that you need to put in to make 1 kilogram 1 degree hotter is called the specific heat capacity. It's how much energy you need to put in to make 1 kilogram 1 Kelvin hotter. Yeah. So for a metal, is this big or small? Small. But for a plastic, it'll be big. Okay, so write that definition down. Yeah.
The amount of energy needed to increase the temperature of 1 kilogram to substance by 1 degree Celsius.
Yeah, now the reason I deliberately didn't say kilogram and Celsius, you notice I said unit mass and unit temperature, because some people use kilograms and Celsius, or you could use kilograms and Kelvin, or like in chemistry I think you would use grams and Kelvin. So this is why I didn't specify kilograms, I just went with unit mass. Now if you went with kilograms in the exam, totally fine. Two from three Starbucks today.
What?
2 Starbucks. No
Yeah.
3.
And
What did you get? Latte?
Yeah.
You like it?
No.
It's my favorite.
Just
Yeah, it's delicious.
I like.
You what? You don't like milk?
Yeah.
What's wrong with you?
Just don't like it.
Don't like milk?
Yeah.
I love milk.
I
Love it.
maybe finish the cup of 2 weeks of milk.
In 5 days, I would drink 3 liters.
Oh.
Delicious milk. Yeah.
Can you
Good.
explain again why plastics
Plastic.
Yeah. For plastics is stronger or bigger, for metal is
Yeah, so what's happening, you know from chemistry that plastic is an insulator. So an insulator means that when you put energy into it, the temperature will change slowly. So like for example, like here's the heater here. If I put plastic here and metal here, which will get hot first? The metal. Because it's a conductor, it's easy for it to take the energy. Not like the plastic. Yeah.
so depends on the material.
It depends on the material, yes. And it's different for each material. Yeah? Okay. Continue? Yeah. Let's look at the units. Okay, so what would be the units here? Well, it's energy, so it's joules, isn't it? But it's not just joules, it's joules for each kilogram for each Kelvin. So what would be the unit, do you think? Joules per kilogram or Kelvin, yeah. So, I mean, if you want to write that down, you can. Some people, you can write joules per kilogram per Celsius, but we prefer Kelvin. Okay, continue. Alright, so, if you think about it this time now, if instead I have oh sorry, I forgot to say that, what did I say it in the previous slide? Yeah, the letter we use is C for this. Okay. So this time we have M, and this time we have delta theta for the change in the temperature. This is in Kelvin, and this is in kilograms. So here we have to put in some energy, delta Q. So the question is, how much energy? Well, if we had 1 kilogram at 1 degree, how much energy would we need? You would only need C. Remember? C is when you have 1 kilogram and 1 Kelvin. What if you had 2 kilograms though? Then you would need 2C. What if you had 1 kilogram but you wanted 2 increases? Then you would need 2C as well. So maybe it won't surprise you if I tell you the formula.
Wait, what is C again?
specific heat capacity. The definition you just gave me 5 minutes ago. The formula is mc delta theta, the change in the temperature. We'll try not to use T for temperature because usually we use T for time. So this is the formula. That shouldn't be surprising, I hope. Delta theta is the increase in the temperature.
So the unit is Kelvin?
For which? Oh, yes, Kelvin, yeah. Yes. Yeah? Okay. So let's have a look at some specific heat capacities for different materials. So the first one is water. So if you have 1 kilogram of water, how much is 1 kilogram of water? Maybe that much. That's 1 kilogram of water. And you want to increase its temperature by 1 degree Celsius or Kelvin, you will need 4,181 joules to do that. If you have ice needs 2,110 joules. Steam needs 2,080. Copper, only 385 because it's a metal. Milk, 2,850. Alcohol, 2,300. Lead, 129. Air, 1,012. Okay, so you'll need these values if you can write them down, please. Yes. Huh? When you make tea and it comes off the water at 100 Celsius. It's gas. You know. Look. Here's your cup. Steam. Yeah. Gas. Hot gas. Question, Amanda?
What is LED?
Lead. It's on the periodic table. I think it's PB. It's what used to be in pencils a long time ago. Lead. Kind of. Nowadays it's not lead, but a long time ago, yes, this used to be lead. Lead is like this. Now this isn't lead anymore. It's carbon now. But maybe your grandfather used lead. It's like carbon. It's soft and it's black, and they used to use it in guns for the bullets a long time ago.
Oh, I know what it is.
You know it, yeah? Yeah? You know it?
So it's also metal. Yeah.
Lead's a metal, isn't it? Yeah. Is it a metal? I don't think it's a metal. Is it?
I think so. I need to see the periodic table.
Yeah. Have you got one?
No.
Oh,
Oh wait, I do.
God, check it first. I don't do chemistry, so I don't need to know this. Well, if it's not a metal, what is it then? It has to be a metal, doesn't it? PB.
PB or PB?
B. Chin?
Yes. Chin.
Chin?
Chin.
Oh, flat. Chin?
No.
No, terrible. Terrible Chinese.
That usually is like money.
What I said was money.
Yeah.
Alright, well that's good too. Did you find PB?
Yeah.
It is
It's
a...
a metal.
It's a metal, okay.
Do you know how to say gas in Chinese?
What?
Gas.
Really?
No.
So you know this one.
No. Gas. Tea.
Cheap?
Yes. Gas.
Cheap. Alright, I'll remember that.
Do you look at Kung Fu Panda?
Kung Fu Panda?
Yes.
Ah.
The tea.
Ah, okay. So,
Mushroom tea.
I never watched Kung Fu Panda. I'll have to watch it then.
Yeah.
Now, notice lead, how much smaller it is compared to, say, water. So lead, it's very easy to increase its temperature. You only need 129 joules per kilogram of lead. That's not much, only 129. It's very easy to make it warm. Okay, continue. So, here's my question. Why do different materials have different heat capacities? What do you think? Why is lead, like what makes lead so small and what makes water so big?
The conductivity.
Oh yeah, but why? Why is the conductivity different?
Chemical bond.
It's complicated. It's complicated and we might look at it later. Maybe. But the reason is quite complicated. Okay. So let's have a look at our first example then. So my question is, how long would it take to boil enough water to make a cup of tea by using a small 1 kilowatt electric kettle? Now I don't give you all the information because I wanted to try and guess some of the numbers, you know, make it like a real life problem.
The KW is
Kilowatts.
what?
I should be a big W, I'm sorry. KW, kilowatts. You remember? Kilowatts? Yeah. Got this? Whew, okay. Let's have a look at it. So, do you all know what an electric kettle is? Do you know electric kettle? I'll draw it for you. You have it at home. Hang on, I'll draw this nicely. No, you couldn't know it already. Really? Alright. I don't believe you, but okay, thank you for being so kind. And then you have the water here. And then it's plugged into the wall. Electric kettle. And the power is 1 kilowatt. So the power is 1000 watts. Yep. You don't need to draw the kettle. Okay. You're drawing it? Okay. Now, you want to make a cup of tea. So, how much water will we put in?
About
500 meters.
500 meters? A lot of water.
half a liter,
Yeah, but what's that in kilograms?
half a kilogram.
Half a kilogram maybe. So we'll put in 0.5 kilograms. Now, what's the temperature of the water at the start? Roughly. The water from the tap. Ah, it's not that cold.
20.
Oh, it's not that warm.
What?
You go to the kitchen and you take, 10 maybe, I think. Yeah?
And I think that's super cold. Is it not?
But when you get water from the cold tap,
From a cold tap.
well, that's what you use, isn't it?
We have both hot and cold.
Do you put hot water when you make your tea, or cold water?
Hot.
Oh, don't use this.
Why?
Do you know why? Do you use hot or cold water to make tea? Yeah, the first part. Do you use the cold or the hot? You too.
Oh, I think it's solar this before because cold water boils faster.
Before you boil it, do you put in cold or hot?
Cold.
Cold, good. Good. Sophie? Oh, good. We have 2 people there. Okay. Andy?
Yeah, cool.
Oh, good.
Yeah.
Do you know why you shouldn't
I
use
know
hot?
why you solar before.
Why?
It takes a longer time to boil cold.
No, that's right. I'll tell you why. So in your home, you have 2 water supplies. The first one, hang on. Come on. It stopped. No, don't worry. I'm sure if he goes to the hospital today, he'll be okay. Let me just return on my pad. Come on. Yeah, there we go. It's back. Okay. So, in your home, you have the cold water that comes from the mains. And this cold water goes into the cold tap. And then some of this water goes up to a tank in the roof. And this water in the tank then can be heated in the boiler. It heats the water, and then this will come out as hot water. So the cold water always comes from the outside, so it's fresh. But the hot water comes from the tank. And you really shouldn't drink this because the tank is open. You know what I mean? So, for example, if a little bird flew into the roof, you may be like, some nice water. Or maybe a little mouse has a little bath.
Oh my god. That's the water we shower in?
Yes. Now, as the shower, it's fine, but don't drink it.
Oh my
Yeah.
god.
Uh,
But I thought
But
it
you're
was
fine. Oh wait, you talked, didn't you?
I always drink the shower water.
I wouldn't recommend it.
I thought it was safe in Europe to drink the tap water and
It is.
shower water.
The cold water. Don't drink the hot water. Because the hot water, maybe the hot water is in the roof for maybe 2 days or 3 days. It's not fresh. You actually look a bit sick, actually. Now that I look at you. Okay, so if we use the cold water, Irene, don't worry. You look worried. No, it's fine. It's fine. I'm just saying, it's better if you use the cold water because it's fresh.
yeah.
Don't. You're not going to worry about this, are you? No, okay. Just in future, use cold water. Okay. Right, so what's the temperature at the start? We'll say it's about 10 Celsius. And the temperature at the end, if you want to make tea, what do you think?
80, 100.
Probably be nearly 100, wouldn't it?
Yes.
Yeah. So what's the change in the temperature? 90. Okay. Right, so we have delta Q equals mc delta T, which equals 0.5. What was it for water? 4182, was it?
4181.
4181. Yes? And then the delta T, delta theta is 90. So we need 0.5 multiply 4181 times 90. So we need 188,145 joules. It's a lot. It's a lot. How long will this take? Well, we can use power equals work over time. So time equals work over power. 188,145 over 1,000. So the time is 188 seconds. Or if you want, that's about 3 minutes and 8 seconds. So about 3 minutes. Yeah. So it takes about 3 minutes to boil the water. Yeah. Seems like the right answer, doesn't it? 3 minutes? Yeah. Okay. No? I think 3 minutes is good. Okay. Continue? Right. Okay. Write this one. Actually, I think you could try this one for me. It's easier than the last one. See if you can do this one. Anybody finished? Sophie? Finished? Yeah. What answer did you get? Sounds right. The unit? Anyone else get an answer? Nearly? It's ice.
Yes. But don't tell me.
I won't tell you. I'll just draw on ice.
You should use blue.
Yeah, I should actually. Oh yeah. Very nice, I think. Okay, got an answer? So what's the delta theta? 9. So delta Q equals MC delta theta, 0.1. And what's the C? 2110. So the answer is 1899 joules. Okay. Yeah?
But it's not joule per kilogram.
No, because this is how much energy in total, so it's joules.
But it's the same, right? That the heat capacity,
The specific heat capacity is joules per kilogram per Kelvin. But this is joules. Yeah. Yeah? Okay. Right. Try, yes. Be brave and try it. Be strong. Who feels brave? Anyone has the answer?
think, just give us a few more minutes.
You think you can get it?
Yeah.
Oh, good. So you have an answer? No. Grace?
And that
You got delta Q? Good. So you have the power here is 3000. Ah, yes.
Yeah, I think I got answer.
Okay.
Woo.
I'll give you a minute. Ready? Okay.
Can I tell you my answer?
Now, wait, let's do it together. So how big is this room? I said 10 by 10 by 5, wasn't it? So the volume is 500 meters cubed. What's the density?
1.
1. So density is mass over volume. So mass is density by volume. So what's the mass?
500 kilograms.
500 kilograms. The temperature is to go from 10 to 20. So what's the delta theta? 10. And what's the C?
1012.
1012. Yeah? Okay, so the formula is delta Q equals MC delta theta, which is 500 times 1012 times 10. 500 times 1012 times 10. So that is 506,000 joules. But the power is 3000 watts. Power equals work over time. So time is work over power. So then the time is 506,000 over 3000. .1 minutes. Great. Now this problem is not very realistic because if you think about it, the heater, like this room here is about, it's about 10 by, I know it's not 5, but I know it's about 10 by 10 by 5. So if the temperature is 10 Celsius and we want 20 Celsius, and this is 3000 watts, it'll take 28 minutes. Yeah? Now, there is problems with this. So for example, some of the heat will be lost when it leaves the room. And some things like the table and the wall, maybe they need more or less than air. So will it be bigger or smaller than 28 minutes? Really? Bigger. Yeah. But I think this here, this is probably more than 3,000. This is probably more like 6,000. The 3,000 is usually for the, the small heaters, the electric heaters is 3,000. But this could be, it could even be 10,000. Yeah. So then maybe 28 minutes is actually accurate. Yeah. Okay. Okay, try this one. 2 more to go. The latte question. Yep. I think I'll do it, but I want you to write it down. But I'll do it now. I'm getting cold actually. Maybe it's back on. Because I was warm at 9 o'clock. Ready? Oh, Andy.
Yeah.
How's Pony?
Why do you know?
Just wondering.
Wow.
So are you and Pony together?
Sorry?
You and Pony
Yeah.
together?
Yeah.
Oh.
Long time.
Really? Long
Yeah.
time?
Yeah.
Since when?
Like it's since January 19.
January when? Oh, that's not that long. January.
Yeah.
No, sorry.
January. February, March, April. I don't think that's that long. Long time, yeah. Alright, have you got this one? I see those two. They have girlfriends. What about up here? No?
I want a girlfriend.
You want a girlfriend? Yeah. No boyfriend, no?
Yeah.
Yeah, the choice is quite bad. You haven't got a good choice behind you. No.
I should be more handsome.
You should look at maybe the science students, I think.
Sorry. January.
It is January. All right, okay. Don't forget that. All right. Now, let's have a look at this one. So.
Yeah, but now it's like 90.
Yes.
97.
Okay. Now, for this one, it's a little bit different because now there are two things being mixed together. Okay, so, oops. How much, well, here's my coffee here, my cup. So we have some coffee at the bottom, and then we have some milk on the top. And I know it's mixed together. But before it's mixed, what is the temperature of the milk? Its temperature is hot, 80 Celsius. And what's the temperature of the coffee? No, the milk is 27. Sorry, and the coffee is 80. And how much milk do I have? I have 200 grams. And then how much coffee do I have? 50 grams. So that's okay, isn't it? And then what happens is they mix it together, and here is your latte. Latte. Delicious. So it's mixed together. So for my picture, I'll draw them separated, but in your mind they're mixed together. So the coffee is there, and the milk is here, but they're mixed. Oh, and what's the heat capacity for the milk and the heat capacity for the water? The coffee, I mean, which is the same as water. 4181, and for the milk?
4181.
The milk? It's not that.
Is it not the same?
No, the milk is
2850.
2850. Joules per kilogram Kelvin. Joules per kilogram Kelvin. Huh? This is the milk. Yeah.
How is it significantly different between milk and water?
It is a big difference, isn't it? The water is nearly,
Twice.
well, maybe not quite twice, but the water is at least 30% more than milk. So like I said, it's complicated. But milk is quite different to water because it has fat in it. Also, milk, it must contain stuff which is easy to heat compared to water. I don't know what, you'll have to ask the biology teacher. I don't know. But milk doesn't need as much energy to get hot compared to water. I couldn't find what the number for coffee was online. So that's why I said use coffee as water. I couldn't actually find what it is for coffee. And also it depends on the coffee. If you use espresso, Arabica beans, Robusta beans, I don't know. So I just said it's the same as water. Yeah. I mean, if you think about coffee, coffee is water and a few beans, so maybe it's like water. Okay, so what's going to happen to the milk? Will the milk get hotter or colder? What do you think?
Hotter.
No. What will happen is the milk will get colder because, oh sorry, my apologies. The milk will get hotter, yes. The milk will get hotter, and then the coffee will get colder. Until they're both the same temperature, I'll call the temperature X. No, not as fancy as that. So the milk gets hotter and the coffee gets colder. Do you understand that?
Yeah.
The energy that the milk gains will equal the energy that the coffee loses. That what has happened is that the energy from the coffee has just gone into the milk. Does that make sense? That you're not making energy, it's just some energy from the coffee moved into the milk. Because the milk is colder, so the heat from the coffee moves to the colder milk. Yeah?
Yes.
What law is that? It's also conservation of energy. It's the second law of thermodynamics. Okay, so do we know the mass of the milk?
Yes.
Yes, we do. So I'll just write M for milk. Actually, I need to make a bit more space. Okay. What's the mass of the milk? 0.2. What's the heat capacity of the milk? 2850. Now, what's the change in the temperature for the milk? Well, previously it was 80, and now did it increase or decrease? Guys, the milk, will it be more or less than 80?
Less.
Sorry, why did they say 80? Nobody's correcting me. The milk is 27.
Yeah.
Will it be more or less than 27? Be more. So the x is bigger than the 27. Yes? So I'll put in here x minus 27. And then here we have m, which is 0.05. C, which is 4181. Now what's the t, the theta? Here it was 80. Will it be bigger or smaller?
Smaller.
Yeah, 80 minus x. So we get
Or like, isn't milk is X plus?
now no, the x is the final temperature. That would be, the x is between 27 and 80. Yeah. 5.4 equals minus, no, sorry, not this. 16724 minus 209.05 x. So the x equals I made a mistake. Let's try that again. Wait, why did I write minus? Oh yeah, because minus is here, sorry. 209.05. Oh, I think this number here is wrong, sorry. It's not 5.4. What should that number be? Not 5.4. I didn't get that right. It should be 0.2 times 2850 times 27. Yeah, sorry, it should be 1. Get my pen back. 15390. Okay, let's try that again. Okay, so we get an answer of 41.2 Celsius when you solve for x. I don't need to show you how to solve that. You'll make Joan very sad if you don't know how to solve this. Yeah, is that one okay? Yep, okay, next. Okay. No, it's not that bad. Much. Now, write this one down, and maybe you could try it. I think maybe I should improve my English. The when, if you could change it to after. After it strikes the wall. Yeah. When? Yeah. After is better. Okay, try it. But before you try it, let's have a little hint. So look, here's the bullet, and it's traveling. What energy does it have? What energy does this have as it's traveling? Kinetic energy. And then when it hits the wall, does it have kinetic energy? No. So where did the kinetic energy go?
Sound.
No. Well, not
Maybe.
heat. So the kinetic energy becomes heat. So what I want here is how much warmer. I want the delta theta. You understand? So I think you can do this one. Maybe.
What's the formula for kinetic energy again? Half mv squared, right?
Not even going to answer that. Feels like I'd say 7,000, maybe 8,000. Finished?
I got 38.76.
What did you get? 16? 60? And you got 64, and you got 38. So he... Uh-oh. Maybe they're both wrong. Maybe. It sounds like, Grace, you forgot maybe the half.
Half 50 joules.
You got 50 joules? What did you use for the heat capacity? For lead, heat capacity, the C? Is that what it is, 129? Oh, maybe a calculator mistake. Let's have a look at it. So, here's the bullet here, and then here it is, it hits the wall. The energy here is a half mv squared, and the energy here is delta Q, and they should be equal. So a half mv squared equals mc delta theta. So in fact the m is not important. I can divide by the c, and I get delta theta is v squared over 2c, which is, so actually this is 10 grams. Don't need to know it, do you? We do.
Yeah.
How? The m's cancelled.
Oh, yeah.
That's smart. In fact, you need the m if you want to work out the number here, which you said was what, 50 or something? Anyways, what's the V? 100. 100 squared over 2 times, and what's the C?
1 to
1
9.
to 9.
Wow, this is interesting. The answer is 38.8.
0.7.
Yes. Wait, who said that? Was it you or?
Not
Okay. I guess they were right.
I
What was your mistake?
don't know.
Calculator?
I can see.
That would be a problem. Yes. That's a lot. Think about this. When you put the bullet in the gun, it's cold. And then when it hits the wall, it's an extra 39 Celsius warmer. So, for example, when you put the bullet in the gun, what would be its temperature? What would you say? Here, we'll say like maybe 20 Celsius. So here, it will be 58.8 Celsius. It'll be this much extra. So in the movie when they fire the gun and it's cold outside and then you see all the steam coming from the blood. That's because the bullet is so hot.
So the heat is inside the wall.
Yeah, well it's in the bullet.
In
And
the
then
bullet?
and then the
So
heat.
you say it's 30.
The heat is in the bullet. So the bullet now is 58, but of course the heat will spread out and make the wall warmer. Yeah. You've seen this. I'm sure you watch action movies.
Yeah.
You've seen and then the steam comes out everywhere. Okay. So there's still 10 minutes left, so you can actually start your homework then. Maybe you can get some of it done now.
Maybe we can go pre-chemistry.
Yeah.
Wait, what?
Oh yeah,
Pre-
we have to
chemistry.
freeze our chemistry.
You have 3-hour chemistry.
No, we have to freeze our chemistry.
Laboratory.
Yeah, lab
Chemistry
report.
report.
And when is chemistry?
Afternoon.
What time?
2 o'clock.
But
Loads of time.
that's like easy. Everyone. Although they want to just see Facebook or Twitter. And sit down on the laptop.
Yeah.
Doing or
Think
computer.
of the children.
Wait, so do you want to...
Yes. Yes.
Sorry, I see you packing up before I even ask. You want to leave to print, is it?
Yeah. Thank you very much.
Fine.
Yeah.
Fine. Oh, I'm too kind. Too kind.